So now I'm going to go over a set of problems to show you how the general addition and general multiplication rules work. Let's go back to our survey of college students and their dorm rooms, and I still have the same numbers as I did before in the last video. This question asks, what's the probability that a randomly selected dorm room has a refrigerator but no TV? Another way of saying this is that you have a refrigerator and no TV. So to calculate this probability, you want to consider all the people that have fridges, but you want to subtract out the ones that have both a fridge and a TV. Then you'll be left with just the people that have a fridge but no TV. So these are our proportions. 0.39 is the proportion of people that have refrigerators, and we're going to subtract out the proportion of people that have fridges and TVs, which is 0.20. We calculated this second proportion in the last video, so take a look back at that to see where this came from. When you subtract that from 0.39, you get 0.19, and that's our answer. This last question is a little bit more complicated. It's asking us for the probability that a randomly selected dorm room has a refrigerator or a TV, but not both. So we're going to use the general addition rule, but we're going to have to subtract out the people that have both a refrigerator and a TV twice. That way they're not counted at all. So the way we want to think about this problem is the fact that we're looking at people with both a fridge and a TV, and we're counting them twice. Once when we count all the people with fridges, and once when we count all the people with TVs. So this first part, the 0.39 plus 0.60 minus 2.0, that is having a fridge or a TV. But we want to subtract out the people that have a fridge and a TV, and that's 0.20. So we're subtracting them out twice because, again, we've counted them twice in these first two numbers. And so the final answer is going to give us 0.59, which is the correct answer. This last problem uses the complement rule a lot. So it's asking what's the probability of having neither a refrigerator nor a TV. So we want the complete opposite. So the complete opposite of having no TV and no fridge is that you either have a fridge or a TV, or maybe both, which is included in this. So we're going to subtract having a fridge or a TV from 1, and that's going to give us the complete opposite of having no TV or no fridge. So we've calculated the probability of finding a fridge or a TV, and we've done that in the last video. So take a look back at that last video, and you'll see that the probability of having a fridge or a TV is 0.79. And when we subtract that from 1, we get the probability of having no fridge and no TV, which is 0.21. Now let's quickly go over a few problems in which we use the general multiplication rule. Remember, a few instances we talked about that the general multiplication rule is used a lot is with drawing without replacement. So now let's go over a problem that deals with that. So let's say, for example, you have a pile of batteries, 9 batteries in fact, and you know that 6 are bad and 3 are good, but you just don't know which are the good ones and which are the bad ones. So you draw 3 batteries out to test them, and you need to know what's the probability that the first good battery you get is the third battery you tested. Another way of saying this is that you want the first battery to be bad and the second battery to be bad, and the third then is good, so that the third battery that you test is the first good one that you get. We're using the word "and" here so we know that we're dealing with the multiplication rule, but we're not putting the batteries back, so we're dealing with sampling without replacement, and so we're going to have to use the general multiplication rule and account for the fact that we're removing batteries. So for the first battery, there were 6 bad batteries out of the 9 batteries we selected, and so the probability of the first one being bad is 6 out of 9. For the second battery that we select, there's only 8 remaining batteries, so that's our conditional probability. And since we've removed one of the bad batteries, we now only have 5 bad batteries left. Finally, for the third selected battery, there's only 7 batteries remaining, and there are 3 good batteries still in the pile. And so again, we're dealing with that conditional probability because we're dealing with the fact that we're removing batteries and not replacing them into our pile. And so we can simply multiply these together. That's what our general multiplication rule says. And when we do this, we get an answer of 0.179. So now you see the general multiplication rule, but let's try another problem just so you fully understand it. Again, we're drawing 3 batteries, but this time we want to know what's the probability that your batteries are all good. Another way of saying this exact same thing is we want to know the probability that the first is good, and the second is a good battery, and the third draw is a good battery. So we need to account for the fact that we're again removing batteries and not putting them out. And so you can see the denominator in all of these is getting smaller because we're always removing one battery. We're also removing one good battery, so the numerator also goes down by 1. Here we start out with 3 because there are 3 good batteries, and then there are only 2 when we've taken one out, and then there's only 1 remaining for that third draw. When we calculate this out, we'll see it's 0.0119, and that's our final answer. This last problem then looks at the complement rule, and you can tell again that it looks at the complement rule because it has the words in it, at least one. So this question is asking what's the probability that you have at least one good battery. And it's easier to calculate the opposite of that, and the opposite of at least one is that none are good. So we'll calculate the complete opposite and subtract that from 1, and that will give us the probability that at least one battery is good. Another way of saying none are good is that they all 3 have to be bad. So I've written this out. The first is bad, and the second is bad, and the third is bad. So again, we're just going to use the multiplication rule to find this second term, which is 6/9 times 5/8 times 4/7, and that takes into consideration the fact that we're drawing without replacement, and that gives us our probability that none are good, which is 0.2381. We'll subtract that from 1, and the final answer will be 0.762, which gives us the probability that at least one battery is good, which is not an unusually low number. So it wouldn't be unusual to see at least one good battery if you were to select 3 of them. Another good way of thinking about the general multiplication rule is through tree diagrams, because the tree diagrams show how events can affect one another. So here we have one event, which is whether or not a person drinks, and the level in which they drink, so it could be binge drinking, moderate drinking, or abstaining from drinking, and whether or not they get in an accident. So whether or not you drink will affect the likelihood that you get in an accident. You can see the accident probability changes in each of these different branches. And so drinking, therefore, affects the likelihood of accidents. And then you just multiply these together to get this last column, which is the general multiplication rule in action. Now let me show you how to create a tree diagram from a word problem. Here we have Mary flying from Boston to Denver with a connection in Chicago. The probability that her flight leaves on time is really small at 0.2. The next set of events is going to tell us whether or not her luggage is going to make it. So if the flight is on time, the probability that her luggage will make the connecting flight is 0.9. But if the flight is delayed, the probability that her luggage will make it is smaller. So knowing that the flight is on time or delayed affects the probability that her luggage makes it. And so therefore these events are dependent. The first set of branches is going to tell us whether or not the flight is on time or delayed. She can only have a flight that's on time or delayed, so these are disjoint events. The next set of paths tell us whether or not her luggage makes it. So her luggage is either going to make the flight or it's going to miss the flight. But these probabilities depend upon which path you take on the arrival of the flight, whether or not it's on time or whether it's delayed. The probability the flight is on time is given to us in the problem. It's 0.2. If it's not on time, it's delayed. And so this is going to be 0.8. Anytime you see branches, they have to sum up to 1 because that's our entire sample space. And we said the sample space has to sum up to 1. The other clue in the wording of the question is the statement if. So anytime you see the word if, it means you travel down one path. So here, if the flight is on time, means we've taken this path. The probability that her luggage will make the connecting flight is 0.95. So the probability that she makes it is 0.95. The probability the luggage misses is 0.05. This last statement then tells us the probabilities on the bottom branch. If the flight is delayed, it means that we've taken this path of being delayed. The probability the luggage will make it is 0.55. And that then also tells us the probability the luggage misses if the flight is delayed, and that's 0.45. So we can fill out this branch from the wording of this problem, focusing on the statements of the if, because they'll be the second branches. So let's go ahead and answer a couple of questions using this tree branch. So this question asks, are the following events independent? The flight leaving on time and the luggage making it to Denver with her. As I mentioned before, these events are clearly dependent because making the flight is dependent upon which path she's gone down, whether the flight is on time or whether it's delayed. If making the luggage making it is the same for both paths, then these events would be independent because it wouldn't matter which path she's gone down, the probability of the luggage making the flight would be the same. But in this problem, they're different, and so they have to be dependent. Now we want to know what's the probability that her luggage arrives in Denver with her. So we'll use the multiplication rule to answer this one. There are two possible ways the luggage could arrive in Denver with her. One is that it could be on time and make it. The other is going to be that she's delayed and the luggage could still make it. And so we're just going to add up those two probabilities. Now we can add these two probabilities because they're clearly disjoint probabilities. Being on time is clearly disjoint from being delayed. They can't occur at the same time. And then the last step is to calculate each of these probabilities. So they have the word and in them. So on time and make it, we can multiply those two probabilities together. And then to get the probability of delayed and make it, we can simply multiply those two probabilities together. The sum of those two probabilities of being on time and delayed will add together for a final answer of 0.63. The last thing I want to briefly show you is how we can get conditional probabilities back from the multiplication rule. Remember I talked about this briefly in the last video, and this probability is really useful because oftentimes we want to know the conditional probabilities because we won't have certain information. So this problem is a really good example of this. Let's say at Dan's diner there are 3 dishwashers, Al, Betty, and Chuck. And Al washes 60% of the dishes, Betty and Chuck each wash 20% for a total of 100%. Now Al's a good dishwasher, he only breaks 2%, and Betty only breaks 2% of her dishes, but Chuck, he's clumsy, he breaks 4% of his dishes. Now you go to the diner one night for supper and you hear a dish break. So you have information. You have the information that the dish has broken, but you want to know which dishwasher was it. Al happens to wash a lot of the dishes, but Chuck breaks a lot, so has a high breakage rate. Who was most likely to have broken the dish? Well, let's just focus on Chuck. What's the probability that Chuck broke the dish? We can answer that question by using this decision tree. Now, I will admit that it's not particularly glamorous, but let me work things out for you. There are 3 different branches that we could go down because there are 3 different possible dishwashers. Al, who washes 60%, Betty washes 20%, and Chuck washes the last 20%. For each of the different dishwashers, then, we have a different breakage rate. So Al breaks 20%. That means 98% of his dishes do not get broken. Same thing for Betty, but Chuck breaks 4%, so 96% of his are not broken. This last number then represents those two paths that they take. So if Chuck is the dishwasher and it's not broken, it's 0.192. Same thing for Al. If Al didn't break the dish, then it would be this path and the not break path, so 0.588. So we can use this decision tree and that formula I just showed you to answer the question of the probability that Chuck broke the dish. So we can think about the formula in this way. We want to know what's the probability that Chuck broke the dish, knowing that the dish was broken. So what we're going to put on top is the probability that we selected Chuck and the dish broke. So that is 0.008. That's the only way that Chuck could have broke the dish. And we're going to divide that by all the ways that the dish could have gotten broken. So Al could have broke the dish, and the probability of that is 0.012. Betty could have broke the dish at a probability of 0.004, and Chuck could have broke the dish, 0.008. So the bottom three numbers represent all the ways the dish could have gotten broken, and the numerator is just Chuck breaking the dish. And so that's going to give us our final probability of 0.33. So as you can see, even though Chuck had a high breakage rate, it was highly unlikely that he broke the dish because he didn't only wash that many dishes. He only washed 20% of the dishes. So that's all for the probability rules that I'm going to cover. In the next set of videos, I'm going to go over random variables, what they are, and how we can use them to get expected values and standard deviations. Now we're going to use those expected values and standard deviations to calculate probabilities, and so that's why these probability rules are important for us.